This is Unit 4, Lesson 5, Part 2, Local Linearization. We're continuing where we left off in the first video by doing some more examples. Example 4, find the linear approximation to y equals 2 to the x at x equals 3, and use the tangent line to estimate the value at x equals 2.97. So what we want to do is we want to find the derivative. We'll have to find the slope and the value of the function at x equals 3, write our local linearization, and then we can use that to approximate the value at 2.97. So our function is, we'll let f of x be our y, which is 2 to the x. If you want to do f of 3 real quick, you get 2 to the third, which is 8. F prime of x, this is one of our exponential derivatives, so it's going to be 2 to the x ln of 2. And so we want to find the value of the derivative at 3. So that's going to be 2 to the third ln of 2. So f prime of 3 is going to equal 8 ln of 2. And while we can use our calculator, we're just going to leave it like that. It'll just save us on decimals for a while. So our local linearization is going to be our slope, which is 8 ln of 2 times x minus 3 plus 8. And I'm going to distribute that, and I'm going to make that my f of x, because that's my local linearization. So I get 8 ln of 2. Well, let me put the x in a better spot. So let's make that 8x ln of 2 minus 24 ln of 2 plus 8. So I kind of have my constants together there. Okay, so now I want f of 2.97. So that's going to be approximately equal to L at 2.97. So substituting everything in, so I get 8 times 2.97 ln of 2 minus 24 ln of 2 plus 8. So putting that in my calculator, I get that f of 2.97 is approximately equal to 7.834, keeping our 3 decimal points. All right, next example. Approximate 2.01 to the fifth. Use your calculator to find the accuracy of the approximation. Is the linearization an overestimate or an underestimate? Explain. So in example 5, they don't really give us a function, but indirectly they do. We can say that f of x is x to the fifth. Since we want to raise a decimal to the fifth power, we can just use that value. So, and we're going to be near x equals 2, so that's going to be 2 to the fifth, which is 32. So we have that. So now we need to take the derivative, so f prime of x. This is a nice simple power rule, 5x to the fourth. I'm sorry about that. I don't know what just happened. Okay, so let's just find our value at x equals 2. So f of 2 is going to be 2 to the fifth, which is 32. And then we're going to find our derivative. F prime of x is going to be our nice easy power rule, 5x to the fourth. So the value of the function at 2 is going to be 5 times 2 to the fourth. So f prime of 2 is going to equal 80. Okay, so now we're ready to find our local linearization. So f of x is going to equal, well, it's approximately equal to our local linearization function, which will be our slope, which is 80 times x minus 2 plus the value of the function at 2. So we want f of 2.01 to the fifth power. That's what we're looking for, 2.01 to the fifth power. So we can approximate that by using our linearization, so substituting 2.01 in for x, and simplifying that, we get the value of 2.01 as being approximately equal to 32.8. So we need the actual value, and then we need to decide if it's an overestimation or an underestimation. So putting 2.01 to the fifth power into my calculator, I can find my error by taking the absolute value of f of 2.01 and subtracting from it my approximation. And then I can see what exactly my error analysis is. So when I do this, I get approximately equal to, and it's pretty close, which is nice. And that's partially because we have a polynomial here, and we're really not moving that far away from our original value. So our error is going to be less than 10 to the negative 2. Now, is this an over approximation or an under? So if you guys can remember what we learned about power functions last year, this is going to look a lot like a cubic function. And so if we're at a little more than 2, we're going to be along that part of the curve. So as you can see, that part is kind of concave up, and the tangent line is below it. So this is going to be an underestimation. All right, so let's move on to our next example. Next example, number 6. Find the linear approximation to g of x equals the cube root of x at x equals 8. Then what we're going to do is we're going to use that approximation to approximate the cube root of 10 and the cube root of 18, and then we're going to find our error analysis. Now we're going to see that we're going to have not very good error percentages. Well, I'm not going to find the percentages, but our power is not going to be as good as it was before, because we're 2 and 8 units away from where we're making our linearization. So let's see how that changes things a little bit. So let's first find g of 8 to find our value for our linear approximation is going to be the cube root of 8, which is 2. And then we have to find the derivative of g of x, which is going to be 1 over 3x to the 2/3 power. So we're going to use that power rule, and we want to remember that this is x to the 1/3 power. So we'll bring that power down, lower the power by 1, and we have this function. So g prime of 8 is going to be 1 over 3, and now I'm going to write it this way just because it's easier for my brain to figure out what the cube root of 8 is and then square it. So we're going to get 3 times 4, so g prime of 8 is going to be 1 over 3 times 4, which is 1/12. Okay, so now we can find our linear approximation, and I'll just put that right down here because we have to do error analysis too, so I'll try to save some space. So it's going to be the slope of our tangent line times x minus 8, and then the value of the function, which is plus 2. All right, so let's go ahead and find first the cube root of 10. Let's approximate that. So we're looking for f of 10. So that's going to be approximately equal to L of 10. So that's going to equal 1/12 times 10 minus 8 plus 2. So that's going to equal 1/12 of 2, so that's 1/6 plus 2. So that equals, let's see, 13 over 6. Okay, and that's approximately equal to 2.1667. Okay, then let's do, let's use a different color here. Let's do our cube root of 16. So that's going to be f of 16 is going to be approximately equal to L of 16. So that's going to be 1/12 times 16 minus 8 plus 2. So this is approximately equal to, if I do the arithmetic here, I get 8/3, which is equal to 2.667. Okay, so what about our error analysis? So let's do that. So let me see here. Let's use orange. Okay, so for that, so for this first problem, it's cube root of 10. We're going to do our error here. I'm going to do this off to the side. We're going to have the absolute value of g of 10 minus L of 10. And so when we do that, this is approximately equal to 0.01216. So our error is not super terrible, but still it's only 10 to the negative 1, which isn't fantastic. And then for our other one, let's change our pen color again to, let's use like this woody color. I think actually that might look too much. Let's make it a yellow woody color. Is going to be the absolute value of g of 16 minus L of 16. And so that's going to be approximately equal to 0.14675. So as you can see, that is not a very good error at all. It's less than a power of 10, so 10 to the 0. So that's not the best error. Okay, so now example 7. See if I can get this all done in one video. I have a feeling that it's going to be a little long, but I'm going to move on. Example 7 says, let f of x be a function that is differentiable for all values, for all real numbers. The table below gives the values of f of x and its derivative f prime of x for selected values between -1 and 1. The function is concave up, which is going to be important, especially if they ask us if we have an over approximation or an under approximation. So we want to write an equation on the tangent line for the graph of f of x where x is negative 0.6. So the nice thing is we have all the information we need right here to write our equation of our tangent line. So our L of x is going to be the slope, which is -2, times x minus 0.6. So that turns into x plus 0.6. And then the value of the function is -51, so minus 51. So part B then asks us to use that to find f of -0.5 because that value is not on the table. So this is going to be approximately equal to our linearization at -0.5. So we're going to take -2 times -0.5 plus 0.6 minus 51. So this is going to equal -2 times 0.1 minus 51. So f of -0.5 is approximately equal to -51.2. Okay, and then part C asks us, is this approximation greater or less than the actual value? Well, it told us in the description of the problem that we had a concave up function. So if that's the case, any tangent line we draw is going to be below the function. So our answer should look like this. Since f of x is concave up on our interval, f of negative, I should have my negative there, -0.5, I should put our approximation. Should say that because it's not the actual value. Our approximation of f of -0.5 will be less than the actual value at x equals 0, negative 0.5. Since the tangent line lies below the curve. Okay, so you're kind of reiterating what it means to have a concave up function and the placement of the tangent line. Okay, example 8. Write the linear approximation equation for f of x equals 1 over x minus 1 at x equals negative 1. And then we're going to find the approximation at negative 1.2. Okay, so we need the derivative. So if you want, I like to do this over here. So f of negative 1 is going to equal 1 over negative 1 minus 1. So it's negative 1/2. And then we're going to find f prime of x. And that's going to be, if you want to think of this function as x minus 1 to the negative 1 power and use the chain rule, we're going to get negative 1 over x minus 1 squared, because we'll bring the power down, lower it by 1. And the nice thing is the derivative of the inside function is 1. So there's nothing really to chain in this one. So then f prime of negative 1 is going to be negative 1 over negative 1 minus 1 squared. So we get negative 1/4. So f prime, I'm sorry, not f prime, f of x is going to be approximately equal to negative 1/4 times x plus 1 minus 1/2. So f of negative 1.2, I'm having trouble with my negative today, is approximately equal to 1/4 times negative 1.2 plus 1 minus 1/2. And simplifying that, we are going to get that f of negative 1.2 is approximately equal to negative 0.45. Okay, so now we're supposed to calculate the error of the approximation. So just to recall, our error is the absolute value of the exact minus the approximation. Okay, so our exact value, if you substitute that in the calculator, is we get a repeating 4.5, a negative 4.5. So we're going to subtract from that. We didn't get a repeating negative 4.5. So that is going to give us 0.0045. So if you notice, we have 2 zeros here, so the absolute value of our error is going to be less than 10 to the negative 2. All right, and then finally, number 9. Given the implicit curve x squared plus ln of x over y equals 1, write the linear approximation of the tangent line. Now, it says it's implicitly defined. We didn't really need that. But one thing we want to do is we have to find the derivative. So let's make this implicit derivative a little easier. So let's rewrite our tangent function. So we're going to have x squared plus ln of x minus ln of y equals 1. So we'll just use our log properties. That way we don't have any quotient rule or anything like that. So taking the derivative, we get 2x plus 1 over x minus 1 over y dy dx. There's our only implicit derivative there. It's going to equal 0. So rearranging this and solving it, so bringing this term over there and then multiplying by y, we get 2x plus 1 over x times y is dy dx. So now we can find our values. So, well, we really don't need to because they're on the graph here of what we want, but we can find the value of the slope. So our value of the slope at 1 is going to be 2 times 1 plus 1 times 1. That's pretty simple. Thanks for choosing 1, 1 as a point. So we get 3 times 1, so our slope is 3. So now we can find our linear approximation. So f of x is going to be approximately equal to our L of x, which is going to be our slope, 3, times x minus 1 plus 1. So there's part A. Then part B says, using the tangent line to the curve, which is on there, what we want to find is this number k here. What is that k? So that a 1.25k is on the curve. So what we want to really find is what is f of 1.25, because that's the x we're at. So we know that that is approximately equal to our local linearization at that point. So, and that is going to equal our k value, because we want this curve to be set up such that that is on the curve. So we want it on the curve. So we're really going to be adjusting the tangent line so that it's on the curve. So it's not perfect. And remember, it's not going to be because these are approximations. So what we have then is that this is going to be approximately equal to 3 times 1.25, minus our 1. We're going to use our linear approximation for part A, plus 1. And that is going to be our k. So when we simplify this, we get 3 times 0.5 plus 1. So that's going to be 1.75 is k. And now we're going to calculate the error, like how far off are we? So what we need, though, is we need the explicit form, because we need to know the value of y at k, the actual value, not our approximate value. So we have to change this into the explicit form. All right, so how do we do that? We'll go back to the form we have here. We're going to use this form right here. And we're going to solve it for y, is what we're going to do. Okay, so we have x, whoops, I forgot to hit my little thing. So we have x squared plus ln of x minus ln of y equals 1. So switching these two, we get x squared plus ln of x minus 1 equals ln of y. So now we have to raise both sides to the e power. And when we do that, what we're going to have then is that y is going to equal e to the x squared plus ln of x minus 1. So now we have an explicit form. So then we can say at x equals 1.25, and we can put that in our calculator. So we can see we can direct substitute now. But you can just put that in your calculator. This is approximately equal to 2.755183. So now we can do our error analysis. Our error is going to be the absolute value of f of 1.25 minus L of 1.25. And when we do that, we get our absolute value of 2.755183 minus our answer from the last part, which was 1.75. So how far off the curve are we? Our error is pretty bad, actually. We are way off the curve. It's approximately equal to 1.005. So that's more than 100% away. So that's pretty terrible. So it wasn't the best approximation. Hopefully this video served to help you understand linearization a little better. If not, we will be going over this in class. and I will gladly answer any questions then.